if you want, I can take it down there too. It's up to you. Probably just off to the side is fine.
See the screen a little better?
Sure.
All right.
All right. So for our next talk, we have a talk on next level testing, and here's James.
Hi, everyone. Thank you. Thank you all for being here today. My name is James Saryerwinnie. I'm a software development engineer at AWS, and I work on the SDKs and tools team. So primarily involved with the Python tooling, things like the AWS CLI, Bodo 3, which is the AWS SDK for Python, and a couple of other open source projects that I'll be using as examples today. So today I'm going to be talking about testing, and in particular, testing that goes above unit testing and integration testing. And the idea is to help us write higher quality software in as efficient manner as possible. And so today I wanted to share a couple of test types that I've used in projects that I found really helpful. And for each of these, I'm going to talk about not only what they are and why you would use it, but also try to give some real-world examples and some tips on how you'd integrate it into your project. One of the things that I always found is whenever I hear about these new test types, they make a lot of sense and I understand them, but it's always a little bit confusing exactly how I can add them to my project or exactly what types of issues they're going to find, so I'll try to give you some examples from projects I work on. Now, with that being said, there's a lot of stuff that I want to go over, so I think we'll just jump right into the first topic here, which is property-based testing. So with property-based testing, the idea is pretty straightforward. You know, here's a traditional test with something like absolute value, and normally what we do with unit tests, we would write specific cases. So we test positive numbers, we test negative numbers, we test 0. But property-based testing is all about giving general statements about whatever your function does. So instead of a specific instance like the integer 3, you might make a statement that says, for any integer you can throw at this function, it should return a value that's greater than or equal to 0. And this is what we mean by properties. And in almost any case, there's always some sort of property you can assert about your test. And if we wanted to do this ourselves and not use a framework, this is a very simplified version of it, but we could just say, let's pick a bunch of random numbers and call it with whatever number we've generated and just double check that the value is greater than 0. Right? This is a very simplified example here, but that's essentially the essence of property-based testing, which is you write assertions about the properties of your functions, and then usually you use a framework to help generate the sample test input. And then one of the great things about the framework we'll look at is that once it finds a failing case, it can simplify it down and try to tell you the minimal input needed to reproduce that issue. So the library that I've used that I really like, and I think is probably the clear front runner in this space for Python, is a library called Hypothesis. And one of the two things that I really like about it is that it has really powerful test data generation. We'll see an example of that in the real-world example in just a minute. And it also is really good about minimizing the errors. So whenever you find an error, it can shrink the input down to just usually a few characters depending on whatever your input is, and it's really nice. So you just pip install Hypothesis. You use your existing test runners. You don't have to use any new executables. You just add it to whatever test suite you have. And to take our first example here, what we had before was a for loop. The equivalent here is just using this given decorator. So this is just in our normal test suite. If you have unit tests, it would just go in that section there. And what we're doing here is we're importing two things, given and the strategies thing. So given is the thing that's going to wrap our test function and give us the looping, and it's actually much more involved than just a simple for loop, but it will generate a bunch of sample test data, pass it to our test function, and then we just assert properties about whatever's been given. Now, so far I've been using this simple integers strategy here, which just gives a bunch of random integers. And the nice thing about this is it's very easy to just try it out in the REPL and see what happens. So here I'm importing integers, and I just call .example whatever my test data is, and you can see it's giving me all kinds of random data, large numbers, small numbers, positive, negative numbers. But the thing that I really like about this framework is it's much more powerful than this. So here's another example here. What we're saying here is we want a list type, and the list can have elements that are either strings, integers, or booleans. And we also only want lists that are less than 3, or max size of 3. And so if we do that same thing with test data, and we call .example on it, we can see we get an empty list, we get a list of booleans with negative numbers, long Unicode strings, so we get all kinds of test data, and it's really composable like that. And you can also plug in your own custom strategies if you want to generate really advanced data structures. So that was the intro to it. I wanted to give a real-world example now. So one of the projects that I started, I think it's several years now, is this thing called JamesPath, which is a query language for JSON. It's used in a couple of products. If you're familiar with the AWS CLI, if you've used -- query to grab instance IDs or state name, JamesPath is the language that backs that. And then also recently was added to Ansible via the JSON query function. It's the same thing. But what's nice about this is it's a pretty standard architecture for a compiler. There's a lexer, a parser, an interpreter, and it's okay if we're not familiar with that. We're just going to look at the first part, which is a lexer. And for the lexer, if you're not familiar with how it works, it takes a string, so in this case foo.bar, and it breaks it up into tokens. So we can see the return value here, and specifically it's a list of dictionaries. And you can see for each type, it gives me a type that says unquoted identifier, here's the value, the next one's a token of type dot, and so on. And then in JamesPath, the last token is always an EOF token to indicate we're done. But right off the bat, if we think about just this, the lexer that takes a string, converts it to various tokens, there's several properties that we can say. So the first one is something that I think no matter what code you have, you can always write something like this, which is you call whatever method or whatever thing you're testing, and it either has to return some type that you expect, or it should raise some specific exception. If it raises anything else, then we're going to say that it's a bug and something we need to look at. So I think this is a pretty straightforward property that, again, really applies to any kind of code you would write. But for a lexer, there's additional things that we can assert. So here's a couple more examples. Let's say if you think about how a lexer works, it tells you where the start of every token is, right? And it wouldn't make any sense to have a token that had the same starting location. That's just not really something that makes a lot of sense. So we can assert that here. Additionally, the way that a tokenizer or a lexer works is it linearly scans through your input. So the starting location should always increase. It would be really weird if you had something at index 0, and then at 5, and then at 2, and then at 1, and it usually would confuse your parser. So we can also assert that the starting locations are always increasing. And we have this all set up. We run this, and one of the bugs that it found was this key error, which, if you're a user of the library and all of a sudden you see key error unknown, I mean, it doesn't make any sense, right? So that's why one of the properties is to make sure we catch any of those errors and raise a proper exception type that has a lot of context about the expression you're parsing and why it failed. And I won't go too much into the details of what's going on, but essentially what happened was there is this tokenizer part here that's supposed to say if it can't figure out what token, the else type is this string unknown. But the problem is that that's not a valid token type. And the proper way to fix this is to use an exception. So if you don't recognize a token, you're supposed to raise a lexer error, and that's the proper way. You're not supposed to return a token type that's type unknown because the parser doesn't understand that. But I think what was more interesting here was not that it caught the bug, because this is now the fix, but it's also a chance to give you design feedback. So what it was saying here was that you're using these hard-coded strings in the lexer and hoping they sync up with things that are in the parser that's indexing into some dictionary there. But it would be a lot easier if you just had a tokens module that actually had a proper attribute. Not only could you get autocomplete, you would get proper errors in the case of just running your unit test, because you would get an attribute error. And you can also get a lot of benefit from tools like PyLint via static analysis that would tell you that this module doesn't have this token called unknown. So there's a couple of other things you can use with Hypothesis. And again, it's really about just making yourself more efficient about the code that you're writing. And a couple of examples. One is using it for refactoring. So even if you don't use it as a final test, one of the things I've done is if you're refactoring and it's a pure refactoring of a function, you can take your old function and you can take your new function and write a test that says anything that I give to the old function should give me the same value if I pass it to the new function. And if not, then it's not a true refactoring, and I might have introduced a bug in the new refactoring. It's also useful for C extensions. So if you have a pure Python module and you have a C extension, you can say for any valid input, if I feed it to the pure Python version and I feed it to the C extension version, then everything I should get the same result. And if not, I probably have a bug, most likely in the C extension. So it's really useful for a number of things besides the traditional types of tests you might think of. So as far as integration with CI, I think what I found is I run this as part of every commit, as part of the Travis build or Jenkins build. The two things that I've run to in practice, since I primarily work in the library space, we support a number of Python versions, which includes 2.6. And Hypothesis is not available for 2.6. There's a separate package that supports 2.6 that I haven't used. But, so I have to exclude it if I'm using 2.6. And the other thing that I've run into is that I think by default, Hypothesis tries 200 test case or 200 examples in that loop. So that for loop would be 200 examples. And I've found that sometimes when I'm testing, I will get some errors that only occur on certain runs of Travis. And to help fix that, if I bump up the number of times up to, in this case, 10,000, that seemed to work. And that I think that made the test run about 30 seconds total, whereas the default is maybe a second or so. And that's something that I've found really useful to make sure that you have reliable runs on Travis CI. And then again, you can just pass that to the decorator for each test function you have. You just pass the settings decorator. Oh, and I should mention the suppress health check was also something that I ran into in practice on PyPy. So I believe if it's the setup or something doesn't occur fast enough, it will time out the test, and so I just have this disabled, and that's worked well for me. So that was property-based testing. Hopefully it gives you an idea of some of the things you can use it for. I found it really, really useful. Now I want to move on to fuzz testing. So fuzz testing is kind of similar to property-based testing, except it usually just gives you a byte stream. So you have some random input data here, and it has this loop, and you call your code under test, whatever that might be. And if you find any kind of unexpected exception, so normally in the fuzzing world it's a seg fault or something, but in Python we're looking at uncaught exceptions that we weren't expecting, then you have a fuzzing failure. And to illustrate this, we'll start again with a simple example before looking at the real world example. Consider this function here. It's buggy. And specifically, if you pass it a string that's length 5 that then has the characters B, U, G, and then G and Y, it will throw a runtime error. And I'm doing this with this nested if-else to show you how fuzzers can really help you out here. But let's say that we didn't use any kind of fuzzing framework. We just wanted to do this with brute force. So a simple way we could do this is start with characters that start with length 1 all the way to 100 and just generate every possible sequence of characters that we could. And in fact, we're only using string.printables, which is letters and numbers and certain symbols. And we try that, and if you do this and you run it, on the machine that I tried it on, it took about 8.5 minutes until it got to character or strings of length 5, until it got to the specific sequence B, U, G, G, Y. So 8.5 minutes to find a simple bug like this. What fuzzers can do is find this a lot quicker. So the one that I've used that I really like is AFL. Stands for American Fuzzy Lop, and it has coverage-guided fuzzing. And what that means is it's able to look at the input it's generating, see what parts of your code get executed, and then use that to guess how it can change its input to further explore your code. And normally AFL is used for C programs, and you can use it to instrument your C programs, and it's also hooks into the compiler to instrument a binary, but there's also a Python AFL. And this is the name of the package you would install. And if you're familiar with the sys.setTrace function, it leverages that in order to integrate with Python coverage data. And the way the fuzzers generally work, and this is the case for most of the fuzzers I've seen, even in addition to AFL, is you have some sort of script, usually some sort of shim that takes input on standard in and then executes your code. And then you also have a set of sample input files. So if you were fuzzing a language, this would be valid programs. If you're fuzzing a file format parser, this would be valid file formats. And it's really used as a starting point for it to start mutating your code. And once you have that, this is all you would need for that same example in Python. You just import AFL at the end, and you have this while AFL.loop. You call your main function. And again, our main function is just reading from sys.standardin. And every time through the loop, sys.standardin will have new input. Now, I wanted to show you an example of how this works. So hopefully we can see that. So this is a video here. And what's happening is it's the same function. This is on the same EC2 instance that ran the brute force version. And as you can see, it's checking for length 5, checking for B, U, and then G, G, Y. Oh, OK. All right, so I'll try to narrate what's happening. So essentially what's happening is there's this input here, this corpus. And what's going to happen, or what is happening, is it will run this PyAFL, and it's a little hard to see, but I just wanted to give you sample input here. So we're saying that the results go to this -O, and then the input comes from this corpus. And if we run this, you might be able to see this. It's kind of dark here, but it'll switch screens real quick, and you can see in probably about a few seconds, it caught the bug. Maybe that's a little easier. And at the top there, it says it took about 3 seconds to run. And for any of the fuzzers, we specified a results directory, right? And in that results directory, there's a crashes directory that says the input that crashed. And if you look at that, it should be this BUGGY down at the bottom. So switching back to the slides here. To reiterate what happened there, when we ran the fuzzer, it created this directory, and in that directory, there were a couple of files there. So anytime it finds a crash, it puts it in the crashes directory, and that input, or that file name has some metadata about where it was in the input, but the contents of that input, or that file, is what caused the crash. And so in that example there, it was saying that this string sequence broke the code. It raised a runtime error. But what I found really interesting about this is that if you look at the Q directory, this Q directory has a number of files, and in that directory has additional inputs that got it further along in the code. So for example, if we look at the contents of these files, we can see that it starts and it figures out that strings of length 5 get me further along in this function than strings that aren't length 5. And then additionally, it starts with B, and then BU, BUG, and eventually all the way until it finds that BUGGY takes it all the way to crashing with a runtime error. So that's one of the nice things about these fuzzers, is they're really smart about trying to explore all the various parts of your code to make sure that you're able to test much more in depth than you could from a brute force, or at least a lot quicker. All right, so as an example of using this, one of the other things I work on is the AWS CLI. And in the AWS CLI, we have this shorthand syntax. And it's kind of a similar thing to JSON. What we found was that if you specify JSON on the command line, it's a little bit awkward with the quoting and depending on what shell you're using. So this is something that's a little less noisy. And we can use that same framework that we saw before, where we just have something that reads from standard in, tries to parse it, and again, has to get a shorthand parse error, or else it fails. And to see this, we took the examples that we have in our documentation about valid shorthand syntax and use that as the starting corpus. Unfortunately, didn't find anything too crazy. The one thing that it did point out, which when you look at it, it's, I guess, obvious in hindsight, but is this max recursion error. So the parser that's used in JamesPath is a recursive descent parser, and of course, with recursive descent, you can hit max recursion. Now, the behavior itself is expected in the sense that, yes, you will eventually hit a limit, but the bug is that this is the error that a user would see, just runtime error max recursion exceeded, and with no context about what happened. And ideally, we want to catch that, say we were trying to parse something, this is what we were parsing, this is what we ran into, and make it a little bit easier for them to troubleshoot. So this fuzzer helpfully pointed that out. Okay, a couple of tips in practice that I found when I run this. So I don't run this as part of the Jenkins or Travis build. It usually takes a really long time to run, and there's a couple of heuristics we won't have time to look at about when you should run it, or when you should stop running it, and when it's found enough. But the two things that I found really helpful is, one, to use the multi-core support. So in that example before, in that video, we were just using a single core, just a single instance, but you can denote one process with -m, and then all the additional ones with -s that are more randomized, but what's nice is they'll all use the same results directory, so when we saw that Q directory that had all the interesting input, all the other child processes can use that as starting points to really explore the space. And it gives a nice increase in the amount of fuzzing it can do per unit time. The other thing that's really nice is the persistent mode. So in persistent mode, normally if you're not using persistent mode, it executes a process and then the process exits. And with persistent mode, what it's saying is instead of exiting, we'll just continue to reuse the same process. Now you have to be careful. In the examples I've been using, those are fine because there's no global state, we're not mutating anything at the module level, and we're just instantiating a new class each time, so that's okay. But if not, then you would have to use the version of this where it just exits the process each time. And I found when you do this, it usually gives about a 3 to 4 times speed up depending on what you're doing, but that was pretty consistent for me. So those are the 2 tips I recommend if you're gonna go down this route. Okay, next one, stress testing. So far, the 2 types of tests we've looked at are really about using the same code but randomized input to try to explore and find issues with your code. This one's a little bit different, and I'm kind of overloading this term here, but with stress testing, the idea is that you take the same input, but you have different execution. So primarily this comes up when you talk about threading. So ideally, yes, I should put this standard disclaimer. If you can use multiprocessing or async IO or something, those are definitely options you should explore. But a lot of times, especially for IO-bound code, threading is a really good solution that works well. We use it a lot. And the example here, I just want to jump into an example, is with streaming downloads. So if you've ever used in the CLI S3CP where you're downloading to the dash means write to standard out, or if you've used download file object to a non-seekable stream, one of the problems with downloading to a stream is that you have to write sequentially. So you can download in whatever order you want, but if you're actually writing to your final stream, you have to write in order, versus a file where you can seek around wherever you want and just write out the bits as they come. So one of the things that we have in our code base is this idea of a sliding window semaphore. And I'll go through this really quickly, mostly just to help kind of get the context of how these tests can help. But this is one point where we really want to make sure we don't mess up any of the synchronization, because you could get into all sorts of trouble, potentially deadlock code or get invalid data. So the way that the semaphore works is if you check out a chunk of a file, so imagine this is a file here. As each thread comes along, it can release a part of the file. Right? And so in this case, one thread might be done with this part of the file, so it releases it. Another part might be done with this part of the file. But you notice the right-hand side isn't moving until the left-hand side is done. So we can continue to remove parts of our file until we finally get to this last part here. Because all the while, there's this thread on the other end that's waiting to be able to write stuff to this file, but it's blocked until the left end opens up. So what happens is once this left end opens up, this whole window is available, which then slides over to this part, and then now the threads that have been waiting to be able to download the second parts of this file can start downloading them. And they call this acquire, which then gives them an integer, which represents what part of the file they can work on, and everything can continue as expected. So the way that we test this is we have this sliding semaphore class, and we specify a couple of things. So we're going to try it with 10 threads and 50 iterations. And for each of those threads, it's just going to acquire a value and then release it, I think 1 millisecond later. And it'll do this for however many iterations it wants, right? And we take all of that, spin up our threads, and we let them go for a while, and we wait for them to finish. Now, with the stress testing, we're not really interested in testing the specific parts during the test. We're more interested in what happens after. So after all this is done, the one thing we can guarantee is that, the two things we can guarantee is that the number of slots available should be our original one. So if we've acquired things and then released them, we should be back to where we started. So we started with 5, so we should be at 5. And the other thing is that if we were to acquire another number, another part of the file, it should be wherever we left off. So in this case, this is the number of threads, which is 10 times the number of iterations that we're going to acquire and release that. So the very next block of the file should be that times the number of iterations. And that's just a good check. So if we were missing synchronization, if we didn't lock something properly, we would likely be off in this number. And that's just a great way to be able to test this type of code. Okay, there's a number of other examples here, but I'm going to leave it at that for stress testing. That pattern generally applies for any kind of threaded testing. There's a couple of other spots we use it, but we run this as part of every CI build, so every Travis build has this. It usually runs pretty quickly. For local development, you usually can run this in a loop with a little bit longer if you wanted to, just have a little more assurance that there's nothing wrong, but in general, we just run this as part of the CI suite. Okay, last one, mutation testing. So the motivation here for this test is that we have been looking at types of tests that help us write reliable code and higher quality code, but what actually tests the test? So as an example, here is a function and 2 tests for it. And if we run this, we feel pretty good, right? 100% line coverage, 100% branch coverage. But if you look at that last test, the test add is false, it's actually not testing what that value is. It's testing that the key is there, but it's not properly testing what the value is. And the reason this matters is, let's introduce a bug. So we're working on the code base. We think everything's great, and we just introduce a typo. Subtle typo, accidentally gets through code review. But effectively, this is just saying x plus 1, right? X minus -1 is just x plus 1. And if we run our test, the test still passed. So we might think everything is good. We have 100% line coverage, 100% branch coverage. We may not actually be even alerted to the fact that our test is missing some things that it should be testing. So this is the motivation for mutation testing. The idea is that you take your test and you take your program, and you modify your program in some small way, usually just one small change at a time, and you rerun your test suite. And if all the tests pass, that means that you were able to break your program or break your code, and no test told you that you did that. What you want to see is if you change your code in some breaking way, you should get a failing test. Doesn't matter what the test is, but as long as something fails, it'll let you know that you're protected against that. And the library that I use for this is a library called Cosmic Ray. It's great, it's really simple. You pip install Cosmic Ray, and then there's really just 3 steps. So you start a session, and you give it some name, my session, and you tell it where your code is and what tests you have, and then you run Cosmic Ray exec with the name of your session. Now this will take a long time. This usually takes anywhere from, it really depends on your test suite, a couple of hours to days. And once it's all done, though, you will have this Cosmic Ray report command that you can use, and it will tell you what it was able to mutate. So with the James Path library, here's a couple of things that it found. We're going to use the lexer as an example again. But in this lexer, it gives it to you in a nice diff format, too, which is cool. It says, here's your original code here, and here's the mutation. So we changed start +2 to start -2, and everything passed, right? And that doesn't seem right. You shouldn't be able to end a token before it started. And potentially, if we had a property test for that could have caught this. But the test still passed. And so if we do it again, it kind of really hammers home the point that you're missing tests, because it said we can also divide by 2, and we can also square the number, and everything still passes. So I think the point is yes, it's missing a test, clearly. Here's some of the other things that the mutation testing framework can do. So it just messes with binary operators, changing in to not equals, equals to less than equals, messing with constants. So you see self.index equals 0 to self.index equals 1, and just runs your test suite to see what happens. So a couple of tips in running this. It's Python 3 only, so you have to make sure that you handle that appropriately, and it has a long execution time. This is not something that I run as part of the normal suite. This is usually just used as an audit. So every now and then we'll run this, see what happens, and if we have missing tests, then go back, or missing gaps, then we'll go ahead and add tests for them or update our tests. And it's really helpful if you have a fast test suite. So it is possible to do distributed test execution with Celery with this. I haven't used that, so I'm not exactly sure what's all involved in setting that up. But if you have a fast test suite, you'll generally get your results faster. Okay, so to wrap up here, we looked at property-based testing, fuzz testing, stress testing, and mutation testing. Hopefully this gives you some interest in exploring these additional test types. Consider adding them to your project. They're very straightforward to add, and I found them really, really helpful in my own projects. Here's some additional links to the projects that I used, and a link to James Path, and that's my Twitter handle if you want to follow me. But once again, thank you, everyone.
So we do have time for some questions. So as a reminder, once again, please make sure that your question is actually a question. And anyone who's leaving, if you wouldn't mind being very quiet if you can. People in the back sometimes have trouble hearing.
So say, for instance, when you're doing the AFL, say in your corpus, say your function takes in some kind of custom object. How would you refactor your function such that the object was kind of taken apart and passed in as parameters? Or would you put a bunch of items in the corpus? How do you handle creating a custom object that gets passed into your function?
So I don't have any experience with that. That's usually where I use hypothesis for that, but then you don't get the benefit of the coverage guided fuzzing. So in my experience, it's mostly been with parsers and with binary formats kind of thing. So you might be able to take a stream and try to use it to then unmarshal to an object, but I've never used it for anything like that, so I can't speak to that.
Thanks. You mentioned continuous integration and also adjusting tests or tweaking things for performance and test runtime. What are your thoughts on how these impact runtime and how that should affect how you integrate this into part of a bigger testing process?
I think in general, if you're using it in a CI system, I really think that it makes sense to try to bump up especially for the random ones like the hypothesis tests and fuzz testing, or not fuzz testing, the stress testing, to bump it up as much as you can. I mean, the more randomized data you get, I think you just have better coverage. One thing that I didn't mention is that usually when we do find issues with this, we convert them to proper unit tests, so you lose the non-determinism part. Like, you want to make sure you have deterministic tests, but it's usually as high as you can comfortably get away with is my suggestion.
Yeah, kind of on that same theme. All these tests that you described, they sound very interesting, and I'm totally on board with I want to use them, but I'm not super comfortable with having non-deterministic tests on part of my CI, right? Because I don't want someone to make a change and then it breaks because of something that just happened to be a weird edge case, and then new contributors, they don't know whether it's something they did. So do you have any thoughts on like how, or especially these ones that are very long, right? Do you have any thoughts on things where you could use these sort of in a parallel track, maybe, like I never found any good infrastructure for maybe running fuzz testing automatically on something like Travis CI, but not so build focused, just for, test discovery.
Yeah, and in fact for fuzzing, that's actually usually what I do. I don't have it as part of the CI suite, primarily just because it takes a long time and you have to look at the data manually. But yeah, I think even for the hypothesis testing, which runs pretty quickly, I also get uncomfortable about having potentially random failures that may not make any sense. The one thing that I have looked at, and I don't think the projects I work on are set up this way, but usually if you at least have it as a separate environment, for something like either Travis or Jenkins, you can say, we're running the unit test, we're running potentially integration tests, and then we're running property-based tests, and make it clear that there might be some element of randomness to it. But in general, with our workflow, the tests get run as part of a pull request or as part of the feature work itself, so that by the time it's merged into master, you just have, there's still a case, of course, that you will get some failures that you didn't see in your normal test suite, or in your normal PR runs, but I think that's just a risk or it's something that it's a trade-off you'd have to consider.
Thanks.
All right, let's all thank the speaker one last time.
All right, thanks everyone. Function, it should return a value that's greater than or equal to 0. And this is what we mean by properties. And in almost any case, there's always some sort of property you can assert about your test. And if we wanted to do this ourselves and not use a framework, this is a very simplified version of it, but we could just say, let's pick a bunch of random numbers and call it with whatever number we've generated and just double check that the value is greater than 0. Right? This is a very simplified example here, but that's essentially the essence of property-based testing, which is you write assertions about the properties of your functions, and then usually you use a framework to help generate the sample test input. And then one of the great things about the framework we'll look at is that once it finds a failing case, it can simplify it down and try to tell you the minimal input needed to reproduce that issue. So the library that I've used that I really like, and I think is probably the clear front runner in this space for Python, is a library called Hypothesis. And one of the two things that I really like about it is that it has really powerful test data generation. We'll see an example of that in the real world example in just a minute. And it also is really good about minimizing the errors. So whenever you find an error, it can shrink the input down to just usually a few characters depending on whatever your input is. You'll only want lists that are less than 3 or max size of 3. And so if we do that same thing with test data and we call .example on it, we can see we get an empty list, we get a list of booleans with negative numbers, long Unicode strings, so we get all kinds of test data, and it's really composable like that. And you can also plug in your own custom strategies if you want to generate really advanced data structures. So that was the intro to it. I wanted to give a real-world example now. So one of the projects that I started, I think it's several years now, is this thing called JamesPath, which is a query language for JSON. It's used in a couple of products. If you're familiar with the AWS CLI, if you've used -- query to grab instance IDs or state name, JamesPath is the language that backs that. And then also recently was added to Ansible via the JSON query function. It's the same thing. But what's nice about this is it's a pretty standard architecture for a compiler. There's a lexer, a parser, an interpreter, and it's okay if we're not familiar with that. We're just going to look at the first part, which is a lexer. And for the lexer, if you're not familiar with how it works, it takes a string, so in this case foo.bar, and it breaks it up into tokens, so we can see the return value here, and specific is, and it's really nice. So you just pip install hypothesis. You use your existing test runners. You don't have to use any new executables. You just add it to whatever test suite you have. And to take our first example here, what we had before was a for loop. The equivalent here is just using this given decorator. So this is just in our normal test suite. If you have unit tests, it would just go in that section there. And what we're doing here is we're importing two things, given and the strategies thing. So given is the thing that's going to wrap our test function and give us the looping, and it's actually much more involved than just a simple for loop, but it will generate a bunch of sample test data, pass it to our test function, and then we just assert properties about whatever's been given. Now, so far I've been using this simple integers strategy here, which just gives a bunch of random integers. And the nice thing about this is it's very easy to just try it out in the REPL and see what happens. So here I'm importing integers, and I just call .example whatever my test data is, and you can see it's giving me all kinds of random data, large numbers, small numbers, positive, negative numbers. But the thing that I really like about this framework is it's much more powerful than this. So here's another example here. What we're saying here is we want a list type, and the list can have elements that are either strings, integers, or booleans. And we also testing and integration testing. And the idea is to help us write higher quality software in as efficient manner as possible. And so today I wanted to share a couple of test types that I've used in projects that I found really helpful. And for each of these, I'm going to talk about not only what they are and why you would use it, but also try to give some real-world examples and some tips on how you'd integrate it into your project. One of the things that I always found is whenever I hear about these new test types, they make a lot of sense and I understand them, but it's always a little bit confusing exactly how I can add them to my project or exactly what types of issues they're going to find, so I'll try to give you some examples from projects I work on. Now, with that being said, there's a lot of stuff that I want to go over, so I think we'll just jump right into the first topic here, which is property-based testing. So with property-based testing, the idea is pretty straightforward. You know, here's a traditional test with something like absolute value, and normally what we do with unit tests, we would write specific cases. So we test positive numbers, we test negative numbers, we test 0, but property-based testing is all about giving general statements about whatever your function does. So instead of a specific instance, like the integer 3, you might make a statement that says, for any integer, you can throw out this function.
Yeah, if you want, I can take it down there too. It's up to you. Probably just off to the side is fine.
See the screen a little better?
Sure.
All right.
All right. So for our next talk, we have a talk on next level testing, and here's James.
Hi, everyone. Thank you. Thank you all for being here today. My name is James Saryerwinnie. I'm a software development engineer at AWS, and I work on the SDKs and tools team. So primarily involved with the Python tooling, things like the AWS CLI, Bodo 3, which is the AWS SDK for Python, and a couple of other open source projects that I'll be using as examples today. So today I'm going to be talking about testing, and in particular, testing that goes above unit testing.